Hello everyone, welcome to our presentation. This presentation is about medical imaging course and our subject is magnetic particle imaging. So let's start with what is MPI. MPI is a new imaging modality that directly detects iron oxide nanoparticle tracers at any point, space and time within the body. Because the tracer is not normally found in the body, MPI images have exceptional contrast and high sensitivity. This allows us to see tracers in cells, blood, and other functional systems within a living organism. MPI was first conceived in 2001 by scientists working at the Royal Philips Research Lab in Hamburg. The first system was established and reported in 2005. Since then, the technology has been advanced by academic researchers at several universities around the world. Now I'm going to talk about superparamagnetic tracers briefly. The SPIO tracer used in magnetic particle imaging is detectable within biological fluids such as the blood. This fluid is very responsive to weak magnetic fields. These particles can be used because the human body does not contain anything which will create magnetic interference in imaging. MPI images are brighter where there are greater concentrations of SPIOs, producing a truly quantitative imaging method. Mixed with other compounds, the tracers can be targeted to collect at a specific location interest, like a tumor. The properties of SPIOs are key importance to the signal intensity and resolution of MPI. Iron oxide nanoparticles, due to their magnetic dipoles, exhibit a spontaneous magnetization that can be controlled by an applied magnetic field. Therefore, the performance of SPIOs in MPI is critically dependent on their magnetic properties, such as saturation magnetization, magnetic diameter, and relaxation mechanism. There are two mechanisms for the relaxation. These are Neal and Brownian relaxation. When entire particles rotate with respect to the environment, it's following Brownian relaxation and it's affected by physical diameter. When only the magnetic dipole rotates within the particles, the mechanism is called Neal relaxation, and this is affected by the magnetic diameter. Now let's look at the recent progress in tracer technologies. In picture A, three different MPI tracers are identical in a standard MPI reconstruction algorithm, but can be observed after applying a multicolor reconstruction algorithm. In picture B, red lung and liver are targeted with two nanoparticles with different relaxation behavior. In standard MPI, the organs are indistinguishable, but after the colorizing algorithm, the organs can be detectable based on the relaxation behavior of the SPIOs. In picture C, SPIO tracers can be designed for multimodality imaging. Mice were subcutaneously implanted with nanoparticle labeled cells and imaged under MPI, fluorescence, and T2 weighted MRI. In picture D, large macroaggregated albumin conjugated to SPIOs are biomechanically trapped in the red lung, allowing imaging of blood perfusion through the lung. MPI images are frequently layered with a CT, MRI, or X-ray image of the patient to show the tracer location in relation to organs or bone. There are several fundamental differences between MRI and MPI. Most importantly, while MRI is composed of signals that form a picture of the body, such as the blood, muscles, and tissue, MPI does not see tissues but creates a fully three-dimensional image of injected tracer particles. Now, Mehmet will explain how MPI works.
Hi everyone, now I'll continue with how MPI works. The basic idea is that an SPIO tracer isn't injected and an AC magnetic field is applied that's called the drive field or the transmitted field, and the SPIO magnetization basically follows the drive field, and then the response is detected as a dm over dt by a received coil. So similar to MRI, we have this AC transmitted field and we are measuring the signal response with parity detection, but unlike MRI, signal is coming from the SPIO. There is not a proton, so there is no resonance. Because of this, we have to do simultaneous transmit and receive. So the magnetization of the SPIO is modeled by the Langevin function, and this is key concept of MPI. So we have this nonlinear response, which is basically result in the magnetization of the particles static trading at a higher field. This is equation for the Langevin function. One parameter that is interesting to notice, which is particle diameter of X function. The nice thing about it is nothing else in the body response like this. So it is the only thing that will have a nonlinear response, and how we are able to produce zero background images. So basic idea is, if you have a big enough dry field that you are applying, the magnetization of the particle saturates, you end up with sort of the square wave like response, and then you can measure the dm over dt value of this wave with the coil. If you look at the Fourier transform, because it's a nonlinear response, you get harmonics of the dry field frequency. You also are going to directly pick up the dry field, because you have to do track simultaneous transmit and receive, and this is not the ideal, because the dry field will be much bigger than the particle response. So to account for this, we use the higher harmonic signals exclusively as the MPI signal, and try to attenuate and ignore the fundamental frequency. If a DC offset is added to the dry field that's large enough, now the SPIO magnetization will be completely saturated, and when you try to measure it, you'll get no response, and so we can take the advantage of this idea for doing this spatial encoding. So we can create a magnetic field that has a field-free region or field-free point. So to use two loops of wire oriented in opposite directions, you can create a field-free point to the center. You can also do this using permanent magnets or answering in opposite directions. So now if you have a particle or group of particles at that field-free region, we will be able to measure this expected response. If the particles outside of the field-free region, the magnetization is completely saturated, and we will not be able to measure any response from these particles. So we explored the saturation for the spatial encoding. Then the idea is, we have this static field-free point, and then we can add a time varying shift field to move the field-free point around in space, and then we can restore it around a region of interest to form an image. We can also do a free line has done a field-free point. So in this case, we can sweep the line across a region of interest, and then we would acquire projection, and then even rotate this and acquire projections to do projection imaging, much like CT. Then to reconstruct the image, you can use a technique similar to CT as well, and this is preferable because it's been shown that you can image with higher speed compared to the field-free point method. So let's talk about resolution. Resolution depends on both properties of particles and also gradient that you're creating with your field-free region. So far, the lowest resolution has been shown experimentally, about 0.5 millimeter in phantoms. So the part that depends on particles can be characterized by the Langevin function. So in this case, Langevin function is specific to the SPIO that you use, and basically determines what saturation field need to be. Then if you can look at the derivative of the Langevin function, you get a basic PSF at the SPIO's its characteristics to your particles. Field-free line or field-free point gradient is the distribution that determines the distance from field-free region in which you get saturation with particles. So you can see how combining these two things will lead to the resolution. So a little bit about sensitivity. The real motivation for using MPI is the promise of higher sensitivity. This comes from the fact that the signal source of MPI is the SPIO magnetization, which is 7 order magnitude greater than the magnetization of protons in MRI. Of course, in MRI, the concentration of protons will be much higher than the injected SPIOs. Now Sena will continue with biomedical applications of MPI.
Hello, I'm Sena and I'm talk about biomedical applications. These two are currently available MPI systems. A is designed for 3D high temporal resolution real-time imaging applications. Scanner is applicable for in vivo imaging from mice to rabbit-sized animal. Generator is equipped with 7 electromagnets. Imaging speed is maximized by using file-free point main magnet, which gives higher temporal resolution than file-free line magnets. It embeds provision acquisition and processing platform. On the other hand, B is magnetic inside momentum MPI system, and it's designed for 2D sensitivity imaging. Scanner is applicable for in vivo imaging of mice. Sensitivity is maximized by using file-free line main magnet, and it gives more signal than imagers using file-free point magnets. This system requires only power and cold water. We can come across with researching applications, and let's deep into them. MPI has perfect potential to image and track stem cells in cell therapy applications. Other imaging modalities are not useful due to have low sensitivity, and iron cannot be detected after islet death. Islet is accumulated cells. Contrary to them, MPI has much higher sensitivity, and released iron nanoparticles are detected even if they are outside of the cell. MPI offers great hope to increase angiographic imaging safety and efficiency, and especially for chronic kidney diseases. Kidney-safe SPIO contrasts are already approved for human clinical studies. MPI has no depth decreasing and no background tissue signal. It's perfectly linear and has nearly perfect signal linearity for detection arterial narrowings. You can see in here an arterial narrowing. Improvements of imaging device have played important role in cancer detection and staging. MPI can be used in cancer detection and therapy studies. It shows the capability to track labeled exosomes in vivo for cancer therapy, but of course more improvement is needed to optimize nanoparticles. Inflammation is involved in any disease process, and detection and tracking of it can help with diagnosis, with monitor and treatment outcomes. Unfortunately, current practice in tracking inflammation often involve biopsies or imaging methods that have low specificity and quantifiability. MPI can be a promising quantitative imaging alternative. Previous studies have shown that use of SPIO tracers to target inflammation. SPIOs may be injected intravenously and may be taken up to inflammation sites. Previous studies have used MR imaging to detect SPIOs for inflammatory tracking. However, SPIOs cause a decrease in signal intensity, and this decreasing could be confused with signal voids from bone or air bubbles. But with the use of MPI, SPIOs can be more specifically detected with higher signal-to-noise ratio. In addition to these applications and researches, MPI offers an exciting array of potential applications. In following slides, I'm going to talk about some feature directions of MPI. Different types of SPIOs with different characteristics and bound or unbound SPIOs can generate distinguishable identical signals. Difference in generated signals can be transformed to multiple color image. In this image, each color shows specific SPIO or a SPIO in a specific state or environment. This creates perfect opportunities to study multiple cell subtypes or target molecules. A multicolor MPI has lots of limitations today, but it could be improved and useful in various areas. It's a goal for MPI community to create an MPI machine that can function as a clinical whole body scanner. But there are some obstacles that MPI must overcome before a whole human body scanner and put into clinical use. But it has been constantly assessed for human practice, as you can see here, some human practice. So it's the end of our presentation. Thanks for listening. There are some questions, and if you want to check yourself, you can stop the recording.